exercise 3. In this section, we will be talking about invertible matrices, and we will define the so-called elementary matrices, and we will explore the connection between these two types of matrices. First, let's define invertible matrices. A is a square matrix n by n, and we say A is invertible if there exists an n by n matrix B such that AB, the matrix product AB, is the same as the matrix product BA, and both of them are equal to the identity matrix. If we can find such a B matrix, then this B matrix is called an inverse of A, and it's denoted by A inverse. This is the notation. The first question that we are going to think about here is the inverse unique or not? Could there be more than one inverse for a given matrix A? So let's suppose there are two inverses. Suppose both B and the C matrices are inverses of A. If that's the case, then B and C satisfy the definition of inverse, right? So AB is the same as BA and it's the same as the identity matrix. Similarly, AC is the same as CA and it's equal to the identity matrix. So this B matrix, we can write it as BAC. BAC, that's the same as BAC because the AC matrix is the identity matrix, right? Now instead of parentheses here, AC parentheses, we can also put parentheses around BA first, right? By the associative property. And if we put BA first in the parentheses, then what do we have? BA will be the identity matrix. So we get, what do we have here? We have here, this is equal to identities and C, we get the C matrix. So what do we have here? Suppose we start with the two inverses, the B and the C. By the definition of inverses, we end up getting the same matrix. B must be the same as a C. So how about the uniqueness of inverse? Yes, indeed, inverse must be unique. So, although in the definition we have defined B is called an inverse of A, it's in fact the inverse of A, because A can have only one inverse. Now let's talk about the relation between invertible matrices and the system of linear equations AX equal to B. When A is invertible matrix, and we would like to know about the solution of AX equal to B. If A is invertible, then we can multiply A inverse on both sides of the equation. Then we know this will give us the identity matrix. So in the end, we have X on the left-hand side and A inverse B on the right-hand side. What can we say about the solution? We have found one solution. A inverse B must be a solution. And how about uniqueness? There's only one solution, A inverse B. So A inverse B is the unique solution to AX equal to B. Now, how about the homogeneous equation? AX equal to 0. Is the solution unique? Well, if AX equal to B has a unique solution, then so is the homogeneous equation, right? The solution will be unique and it's equal to the 0 vector. Yes, the solution is unique and then it's the 0 vector. Remember, we have talked a lot about the uniqueness of a solution for the homogeneous equation. What happens when the homogeneous equation has a unique solution? If the solution is unique if and only if the rank of A is equal to n, if and only if the reduced raw echelon form of A is the identity matrix. These three properties are equivalent. And just now we have shown that whenever the inverse of A exists, A is invertible, then the homogeneous equation has a unique solution. And remember, this is the same as saying that rank A is equal to n, the same as saying that reduced raw echelon form is the identity matrix. So an invertible really means all these things, 1, 2, and 3. It implies all these three properties. Let's consider a few more properties of invertible matrices. Suppose A is invertible and B is the inverse of A. Does it mean that B is also invertible. Is B invertible? Think about this before we continue. What do you think about this? It's indeed invertible, isn't it? And the inverse of B is equal to A. How about A transpose? If A is invertible, does it imply that A transpose is invertible? By definition, BA is the identity matrix and AB is also the identity matrix, right? Now let's take transpose. For this one, BA transpose is the same as identity transpose. That would give us the same identity matrix. And AB transpose is also the same as the identity matrix. The transpose of BA is B transpose and A transpose. Similarly, the transpose of AB is B transpose A transpose. So we can see that the matrix B transpose satisfy the property that when it's multiplied with A transpose at the front or the back, it's the identity matrix. So by definition, do we have an inverse of A transpose here? Yes, indeed. The inverse of A transpose would simply be B transpose. Now suppose we have two invertible matrices, A1 and A2. C is the product of A1 and A2. Is a C matrix invertible? For C to be invertible, we need to find out a matrix. When we multiply at the front and at the back, we get the identity. So let's try to multiply a matrix at the front so that the product is the identity matrix. Suppose we put A1 inverse, then A1 inverse and A1 will cancel off and we are left with A2, right? So let's multiply with A2 inverse, then we get the identity matrix, right? Now let's multiply the same matrix A2, A1 here at the back and see if we get the identity again. And we see that A2 cancel off and A1 cancel off again. So we get indeed the identity matrix, and C is indeed invertible. Yes. And the inverse of C is A2 inverse and A1 inverse. Let's generalize this property a little bit. We have A1, A2 to AK. All of them are invertible matrices. And the C is the product of A1, A2 to AK. Is the product also invertible? We will leave this as an exercise. The second topic in this section is elementary matrices. Elementary matrices. We will be writing these two words a lot, so we will use the abbreviation EM. Definition of EM. An E matrix, square matrix, n by n, we call E in EM an elementary matrix if we can obtain E from the identity IN by a single elementary row operation ERO. For example, n is equal to 3 and we have I3 identity matrix of size 3 by 3, and let's say we perform a single ERO. Remember here it's single ERO, right? So we perform the single ERO of exchanging the first and the third row. If we exchange the first and the third row of the identity matrix, then we get 0, 0, 1. The second row is not changed. Third row will be the first row of the identity matrix. So this is an example of EM. Another type of EM is to scale a particular row. So for example, we use the same identity matrix of sizes 3 by 3 and we scale the second row by C. So the first row and third row are not changed at all. First row and third row as the identity matrix. Only the second row is changed. And the second row is scaled by C. So the second row is a 0 and then a C and a 0. For the third type, another type of ERO is row addition. So we have in this example we multiply the second row by C and we add it to the third row. So the first row and the second row are not changed at all. Only the third row. For the third row, we multiply the second row by C and we add it to the third row. So this is what it is. So the elementary matrices are obtained from the identity matrix using a single ERO. What if we take product of an elementary matrix and an arbitrary matrix? What do we have? Suppose now we have an example of a matrix. It's this one is 3 by 2. The first row is 1, 1. Second row 2, 1. The third row is 3, 0. Now suppose we have the matrix product E1 and A together. E1 is this matrix here. It's obtained from the identity matrix using interchange of rows, row 1 and row 3. And we multiply with A matrix. What do we have here? For the first row, let's try to look at the first row. For the first row, we multiply the first row with the first column. Then we get 0, 0, 1, 0, 0, 1, 1, 2, 3. So we need to put 3 here. And then the second element, for the other element, for the 1, 2 element, we have 1, 2 entry. We have 0, 0, 1 and the 1, 1, 0. Then we get 0 here. Now for the second row, 0, 1, 0, 1, 2, 3. So we get 2. We get 2 here, 2. And this is 1. And for the third row, we have 1, 2, 1, 0, 0. 1, 2, 3. So we get 1. It's a 1. And then it's 1, 0, 0. 1, 1, 0. So we get another 1 here. So what have we actually done? If we would have taken A and interchange R1 and R3, this is what we get. So this is the same as if we take our A matrix, interchange row 1 and row 3. This is what we get. So this is the same as multiplying, taking the matrix product E1 and A together. So the elementary matrix now has a new meaning. Before, when we talked about ERO, we said we interchange row 1 and row 3 and we get this matrix. Now, instead of describing this using words, we can simply do matrix product. If we just do matrix product, we will get the result of interchange row 1 and row 3. Now let's see if we have something similar with E2. E2 is this matrix here. It's obtained by applying scalar multiplication for the second row, and this is what we get. And we multiply E2 and A together, and let's work it out. For the first row, we get the same thing. For the third row, it's 0, 0, 1, 1, 2, 3, 1, 1, 0, so we get the same thing as well. 3, 0. The first row and the third row are not changed. How about the second row? The second row, 0, C, 0, 1, 2, 3. So only this element get multiplied by C. Similarly, for this element here, 0, C, 0, 1, 1, 0. So only this element get multiplied by C. So we get 2C and a C. And let's again compare with what we would have gotten with this operation, this ERO operation, and they are the same thing, isn't it? So again, multiplying, taking the matrix product E2 and A is the same as applying the same ERO that we used to get E2 on A. So this is actually the same as the matrix product E2 and A. Similarly, when we have the matrix product E3 and A, it's equal to, the first two rows are the same, while the third row we have 2C plus 3 and a C. So it's again the same as doing row addition on A directly. It's the same, these two matrices are the same. We have the conclusion that if A is an m by m matrix and E is m by m, it's an elementary matrix resulting from a single elementary row operation on the identity matrix IM, then the matrix product EA can be obtained from A by the same ERO on A. What this means is that suppose we apply an ERO, a single ERO on A, and we get a B matrix. Now suppose we apply the same ERO on the identity matrix IM and we get E, then B can be obtained this way. It can be obtained as the matrix product E and A. This is very interesting. Earlier when we introduced elementary row operation, we describe it by words. Now we can describe it by equation. And remember, Gaussian elimination is a series of elementary row operations. Now we can convert each elementary row operation into a matrix product, and Gaussian elimination then becomes a series of matrix products. Let's talk about some properties of elementary matrices before we come to the point that we just talked about. First of all, is an elementary matrix invertible? We know elementary row operations, they are reversible. Each elementary row operation is reversible. So is the corresponding elementary matrix invertible? For example, if we apply the row interchange, row 1 and row 3 interchanged, and we apply it on the 3 by 3 identity matrix to get E1, we can get back the identity matrix by the same row interchange, right? Now, do we know what E1 inverse is? Pause and think about it. Now, we see that applying E1 to the identity matrix, we get E1 again. And then when we apply E1 again, because from here to here, it's like applying E1, right? And from here to here, it's like applying E1 again. So E1 and E1, we get the identity matrix, right? So we know what's E1 inverse now? E1 inverse would be simply E1. How about this scaling operation? We apply on the identity matrix the elementary row operation of scaling the second row by C. How can we get back the identity matrix again? Pause and think about it. What can we do? We can scale the second row by 1 over C. Then we can get back the identity matrix, right? Now, what is E2 inverse? So this one is E2 here, from here. The elementary row operation can be described by E2. And here, the elementary row operation is E2 inverse. And E2 inverse would be 1, 0, 0, 0, 0, 1. And the second row is scaled by 1 over C. E2 inverse. Now, the last one, row addition. We add C times row 2 to row 3. So now if we want to get back identity matrix, we can simply subtract it. We add minus C times row 2 to R3. So this corresponds to applying I3. And this will be E3 inverse. And what is E3 inverse? That will make E3 inverse look like this. The first row the same, the second row the same, and the third row we add minus c times the second row to the third row. Another question. Isn't the inverse of an elementary matrix an elementary matrix too? Pause and think about it. Ready? If we look at each operation, interchange, scaling, row addition, we see that the inverse, this is E1 inverse, right? E1 inverse, each inverse will correspond actually to an elementary row operation as well. So again, it's an elementary matrix. How about E transpose? Suppose we have an elementary matrix E. Is the transpose also an elementary matrix? The answer is yes. This is a yes, and this is a yes as well. And I will leave the transpose as an exercise. Please work out for each three cases, interchange, scaling, and row addition, what would be the elementary row operation corresponding to E transpose. One more question. Suppose we have an A matrix and the reduced row echelon form of A is this R matrix. Can we find elementary matrices E1, E2 to EK? So all these are elementary matrices for some K. Therefore, we find a number of elementary matrices such that the matrix product A, apply the matrix product E1, A, and then another one, E2, and then all the way to EK. The result is the reduced row echelon form of A. Is it possible to do that? Pause and think about it. Yes, indeed, isn't it? Because we obtain R by a series of elementary row operation, and each elementary row operation can be represented using one elementary matrix. Each elementary row operation can be represented using one elementary matrix. So when we apply a series of elementary row operations to get R, we can simply form a series of matrix product to obtain R. Let's group all these elementary matrices together and call it P. Then we have P, A is equal to R. Is this P matrix invertible? Is this P matrix invertible? What is P? P is the product, EK to E1. But we know each elementary matrix is invertible. So the product is also invertible. So yes, P is invertible. And furthermore, P is a product of elementary matrices.